All right, so today we're talking about geometric mean. Geometric mean is one of these obscure little topics that we're not going to spend a ton of time on because it doesn't really get applied all that often. However, there are specific cases in which it is helpful, and we'll talk about some of those today. So the goal is I can find the geometric mean between two numbers, and I can solve problems involving relationships between parts of right triangles and the altitude to its hypotenuse. So first of all, geometric mean. Geometric mean is the average that indicates the typical value of a set of numbers. Now, this is what geometric mean actually looks like. So the geometric mean of two positive numbers, a and b, is the number x such that a over x equals x over b. And so x squared equals a times b, and x equals the square root of a times b. So setting this up as a proportion, what this could potentially look like would be, if we were to set up this proportion, we'll go with purple today. So if we had, let's just say we were pulling these values from a right triangle and we said A was 3, then we had our X, then we had our X, and then B was, let's just say 12. So what this would look like, we could either cross multiply, in which we would get x squared equals 36, then we would take the square root of both to find out that x equals 6, or we can kind of skip a step and we can jump into this kind of more progressed version, and we could write it out. Instead of writing it as a proportion, we would write it as x equals the square root of a times b. So that would be 3 times 12. And so essentially what this allows us to do on this right-hand side is just go straight into solving for that x in kind of a one-step plug in your calculator situation. We know 3 times 12 is 36. We would just do square root of 36 if we didn't know it off the top of our heads. We would just punch that in our calculator and we'd be done with it. That being said, I think this right way is a good way to skip a whole bunch of writing and a whole bunch of steps. But I would jot down this whole bit in my notes, mainly because it's hard to remember all this stuff, especially when it's just some little obscure piece. That being said, it's going to be on a quiz, it's going to be on a test. If it's in your notes, you can use those. I think it would be beneficial to take the 30 seconds and write it down. But I can't make you do that. So, all right, example problem. So find the geometric mean between 2 and 50. Let x represent the geometric mean. So, like we just talked about, we could either say, okay, 2 is A, 50 is B. Let's set up our proportion. 2 over x equals x over 50. And so we could set that up. We could cross multiply. We could say x squared equals 100, square root both sides, x equals 10. Or we could have just started off and said, okay, x is going to equal the square root of 2 times 50. 2 times 50 is 100. Square root of 100 is 10. My hand's already hitting the side of this, which is a good sign for today. And that is 2 times 50, not 2.50. So we would get x equals 10. In both cases, it's really whichever way you're more comfortable with. That's how you should operate this. So this would be a problem that you guys would work on in class, and then put your answer on Zoom. However, it is B. So now, theorem 8.1. And this is kind of, this is like geometric mean, or I shouldn't say it's like geometric mean, it's kind of a building block. So essentially what this says is, if you have the altitude and that altitude connects to the hypotenuse, and if we remember, the hypotenuse is that side opposite the 90-degree angle, also known as the longest side in your right triangle. So if the altitude is going to the hypotenuse, then the two triangles formed are similar to the original triangle. So in this case, let's get a red here. So, or we'll go with blue first. So, in triangle ABC, that altitude drops down to the hypotenuse, this red line here. So what that essentially says is if we have this yellow triangle, that yellow triangle is similar to this blue triangle, which is similar to this green triangle. So the littlest triangle is similar to the mediumest triangle is similar to the biggest triangle. And then we could write a similarity statement for all three of those. And how I like to do that is I like to orient all the triangles the same way, just because, quite frankly, it's easier for me to see it than that way. So we would say, I'm going to say triangle A, B, C is similar to, so triangle ABC, I go from the skinny side to the short side to the 90-degree angle. So skinny side A to short side C to 90-degree angle D. So triangle ABC is similar to triangle ACD. And that is also similar to triangle CBD. So we could write this similarity statement for all three triangles. So triangle ABC is similar to triangle ACD, which is similar to triangle CBD. All right, so now they want us to write the similarity statement identifying the three similar triangles in the figure. So like I said, I think it's beneficial to redraw these and orient them the same way. So I kept this little picture in here showing that happening, because now that they're all drawn and oriented the same way, for me to write my similarity statement, I don't even have to really think about it. I can just say, okay, triangle EFG is similar to triangle FHG is similar to triangle EHF, because I'm following that same pattern every time, which we have to do in order to write a similarity or a congruence statement. FHG, and it's also similar to triangle EHF. Delightful. Continuing on. So, write a similarity statement identifying the three similar triangles. So, three similar triangles. I'm going to draw these real quick. So, I have my middle triangle, which would be LOM. My big triangle would be LMO. Then my little itty bitty triangle would be MON. All right. So now we just have to figure out which one is correct. So LNM. Oh, I'm sorry. I said silly me. So this one goes LMN. There we go. Wrote that wrong. So LMN. So LMN to MLO. That one's not correct. A can't be right because we went from bottom left to right to up. This one would be LOM if they followed that same pattern. So we know A is false. And then our second one, or no, LNM. Yeah, still false. Sorry. All right. So NML, so top, bottom, left. LOM doesn't follow the same pattern, so it can't be B. C is LMN, so it's going from left to right to top. Left, right, top, LOM. Left, right, top, MON. Correct, so that has to be C. It's always C. We know that. Okay, now we have two more theorems. These theorems are, quite frankly, they're hard to memorize. So I encourage you to please write these in your notes. I beg you, please write these in your notes. I have a note sheet on my little notebook here that you can't see. I have these written down because I know I'm going to need to reference them because I can't keep them straight in my head 100% of the time. So anyway, theorem 8.2, what this one is pretty much saying is that we can set up a proportion that says h squared, or so x over h equals h over y, which is essentially saying h squared equals x times y, which we could of course simplify further to say h equals the square root of x y, as they did here. So if I was writing notes, if I was in your shoes, what I would do for my notes here, I would draw that picture and label it. I would write that proportion, and I would write that as well, the h equals square root of x, y. 100% would do that. I definitely would not just skip over this and move on. I don't think that would be beneficial to you. That being said, I'm going to continue on. So 8.3, if you need to pause the video to write those down, please pause the video to write those down. Now for 8.3, we kind of deal with the same thing but different measurements. So this one tells us that we can write these two proportions. Ooh, that wasn't a very clean circle. We're going to give that one another go. We can write that proportion. We can skip all over this slideshow. We can write this proportion and solve for different measurements. So we can solve for A, we can solve for B. Quite frankly, we could even solve for X or C if we really wanted to, using those proportions. So once again, I would write those two proportions. I would write the two shorthanded ways associated with them, and I would draw that picture into my notes to use for later. I can't write it for you, but I can encourage you to. So let's see what this looks like in practicality and in action. So anytime we're using theorems 8.2 and 8.3, typically if we're going to end up using both of them, we start with 8.2. And what 8.2 allows us to do is to solve for the altitude or the height, being this line labeled E. So what 8.2 says is we can make this proportion x over h, or in this case, x over e, equals e over y. And I'm just going to label these x, y, just so we can clearly see what we're talking about here. So now we don't know our e value, but we do know our x and y. And so I know e squared, because e times e is e squared, is going to equal my x times my y. So 6 times 24 is 144. Then if I take the square root of both sides, I find out that e equals 12. So instead of e, we're going to say 12. Yay. So we have one of our values already. E equals 12. Now, from there are two different ways we can solve from here. Since we've kind of cheated and I've already taught you guys Pythagorean theorem to a degree, I hate when it does this. You could use Pythagorean theorem here to solve for C and to solve for D, but we're going to use theorem 8.3 just to stay with the merits of this lesson itself, using geometric mean. So essentially what we're going to do now is we're going to use theorem 8.3, and what that tells us is either x or y times c, which c in our formula would be this measurement. This would be RC. So x or y times c is going to equal the square root. So the square root of x or y times c is going to equal either d or this c. So it's going to equal one of those. And let's look at this real quick. So I'm going to switch over to green. So my first proportion would look like this. I would say my y value, so 24 over d. So 24 over d is going to equal d over this whole length. So that would be 24 plus 6, which would be 30. So d squared is going to equal 30 times 24. And so the square root of 30 times 24 is going to equal d. So I need to do 30 times 24 in my calculator. Then I need to take the square root of that, which would be 26.8. We're just going to round. So d equals 26.8. All right. Now, just out of my own curiosity, so a equals, oh, I'm sorry, I messed that up. Whoops. So that should have been C, correct? Yeah. See, like I said, I mess these up all the times. So that would be 144 plus 24 squared. Okay, that looks better. Yep. Okay, so here's the mistake I made so we can learn from this. I set this over D when it should have been over that C. So 24 over C equals 24 times be 30. There we go. Okay, so now if we did our cross multiplication, we'd be correct. C squared equals 24 times 30, which would be 720. We take the square root of both sides, and we would get C equals whatever I had written down before, which I've already forgotten. 26.8. Okay. See, and that's why it's important to have these in your notes so you don't mess up like I did. All right. Now we'll move on to our last one. So now we're solving for D. So we would have 6 over D equals D over 30, because 30 is our whole length here. So we multiply those, we get D squared equals 30 times 6, which would be 180. We take the square root of both sides. We do that in our calculator, and we get 13. D equals 13.4. All right, so that is how we apply geometric mean painfully. All right, so now you would give this one a shot on your own. Find e to the nearest tenth. So plus 6 squared, 320 square root. All right, so the answer is C. Lovely. Okay, So Mrs. Al Spatch is constructing a kite for her son. She has to arrange 2 support rods so that they are perpendicular. The shorter rod is 27 inches long. She has to place the short rod 7.25 inches from one end of the long rod in order to form 2 right angles with the kite fabric. What is the length of the long rod? So what we're going to want to do is we're going to want to cut this triangle since it's congruent on each side, like it's a mirror image essentially. What I want to do is I want to cut this just like that. I want to cut it in half almost like we were folding it along that horizontal line. And so when we do that, this is what it's going to look like. So you see we cut this height, this 27-inch height in half, so we got 13.5 for the height now. So what we're going to do is we are going to use theorem 8.3 in order to solve it. Oh no, I'm sorry, we're going to use theorem 8.2 actually. So theorem 8.2, we had the triangle that was labeled like this, x, y, h, and we could write a proportion that was x over h equals h over y. So using that, we know what h is and we know what x is. So we're just going to substitute those values in, and we're going to have 13.5, 7.25 equals 13.5 over y. Then we'll have to solve for y. So we'll have to cross multiply and then solve. So on our right side, we'll have 7.25 y equals 13.5 squared, or 13.5 times 13.5, which would be 182.25. Then we have to divide by 7.25 on both sides. Which would leave us with 25.14. 25.14 inches. All right. Now we have this one that you could give a try if you were so inclined. What is the length of the aircraft to the nearest tenth of a foot? So the length of the aircraft, which would be so a jetliner has a wingspan BD of 211 feet. The segment drawn from the front of the plane to the tail intersects BD at point E. AE is 163 feet. What is the length of the aircraft? Delightful. Okay. 231.